wasn't a nice Friday because I was knocked over, I would have been really bad.
Yes.
Yeah.
Okay, so remember to email me your thoughts as to when you want exams, or exam. Okay. There will be at least a couple-day window so you can choose when you want to take it. All right, so today we're going to do the big three consequences of the argument principle. Okay, we're going to start with Rouché's theorem. And so there are a few theorems in the subject not due to Cauchy and Riemann. This is one of the best ones that does not bear their name. Okay? This is the following. F and G are holomorphic. Open omega. Circle C containing omega. Does it have to be a circle? No, it just makes things nice to say circle. It holds in greater generality. Assume the absolute value of F is strictly greater than the absolute value of G on the circle. Then the number of zeros of F inside C is equal to the number of zeros of G inside C. Alright, so before proving this, let's just look at what's being said. I'm not saying anything about how many poles F has inside C and how many poles G has inside C. Why don't you expect to get any information about that? Yeah, it's holomorphic. There's no poles. What about zeros of F on the circle? How do you think those are related to zeros of G on the circle? Could we have infinitely many zeros of F on the circle?
No.
No, we'd have a
Finite number of zeros.
well, we'd have an accumulation point, then the function would have to be identically zero.
Right.
That doesn't seem to be contradicted here. That would just mean G would be identically zero. What do you know about the number of zeros of F on the circle? So what do you know is happening on the circle? On the circle, what do we know about F and G? I'm sorry, they're holomorphic, but what relationship do we know between F and G?
F is bigger than G.
The absolute value of F is strictly greater than the absolute value of G.
That means
What?
that they can't be on the circle?
So can F have a zero on the circle?
No.
No. What's the smallest the absolute value of G could be?
0.
0. So you know, as the absolute value of F is strictly greater than the absolute value of G, which is 0, you can conclude F is not 0 on the circle. Right? I don't have to put in an additional assumption saying F does not vanish on the circle. I get that for free when I write absolute value of F is strictly greater than absolute value of G. Okay? We are going to prove this by using some of my favorite functions in all of mathematics. What's your favorite function in mathematics? Okay, think more basic.
Z.
More basic, constant.
Oh.
Okay? So I'm thinking of a function. It's real valued and it's continuous. What can you tell me about it? Yes. Right? If I just tell you I'm thinking of a real valued continuous function, I haven't given you that much information. Real valued, complex valued continuous function.
Constant. 0.
Complex valued.
Oh.
I'm not even saying holomorphic, just complex valued. You don't know that much. Alright. I'm thinking of a integer valued continuous function. What do you know?
Constant.
Constant, right? Integer valued continuous functions are constant, right? So what we're going to do is, the way we're going to prove Rouché's theorem is we're going to show that a certain expression is continuous in a parameter and it's integer valued. Well, the only thing that can be continuous and integer valued as a function is a constant function, and that's going to be the proof. So it goes as follows. Let's let ft of z be f of z plus t times g of z. 0 less than equal to t less than equal to 1. So we only look at this for t between 0 and 1, but this would make sense for other values of t as well. You could take t to be complex valued and actually get a holomorphic function out of this. So what we're doing is we're basically interpolating between two functions. Oh, I'm sorry, this is equal to number zeros of f plus g. Sorry. There's two ways of doing Rouché's theorem. I was taught one way, the book is doing the other way. I'm sorry, we want to do f plus g. Okay, so when you look at f plus tg, what's the extreme values? Well, if I take t to be 0, what do I get? I just get f. And if I take t to be 1, I get f plus g. Right? And so we're going to interpolate between the two extremes. And again, you've got to be careful. Different books use different conventions for how they write down Rouché's theorem. Here, we're starting with a function f, and we're tweaking it by adding a function g. Other places say we're going from a function f to a function h. It really doesn't matter what you do, but you should pay attention and see which one you're doing. So let's study the integral 1 over 2 pi I over c of ft of z prime over ft of z dz. What does that integral equal? The number of zeros. Be more specific. The number of zeros is the number of zeros of ft inside C. And this is just the argument principle. And we saw how we could expand this by looking at what's going on. And we have our toy contours, and the idea was every time we have a 0, we have something like this, we come in and we do our stuff like this. So this is just the argument principle. What can you tell me about this number? It's an integer. So all we have to do is show that this integer doesn't depend on t. How do we show it doesn't depend on t? Well, if we can show it's a continuous function of t, the only continuous functions that are integer valued are constant. So what we need to do is look and see what happens if we change t. So I really don't want to use the notation t prime because I've got derivatives going on. So maybe I'll take 2 times t and s. So let's look at n of ft minus n of fs. This would be 1 over 2 pi I, the integral over c of ft prime of z over ft of z minus, we'll indent the contour because it doesn't matter, fs prime of z over ss of z dz. Okay. We need to show that this is continuous. C has finite perimeter. It's some fixed curve. All we have to do is show that if t is sufficiently close to s, that this is small. Right? All we have to do is show that this number, we're bounded by something less than what? What do we want to bound this integral by in absolute value? You could do epsilon, but you can actually do worse than epsilon. This is one of the few times you don't have to be too good. I want to show that this integral in absolute value is less than what number? Less than 1.
Because the integer value?
Yes, it corrects itself. All I have to do is show that it's less than 1, it's an integer, there are not that many integers whose absolute value is less than 1. Okay? There's actually a complete classification of them. So all we have to do is show that this is less than 1. How do we show it's less than 1? We show it's less than epsilon. For small epsilon. But we don't really need to get the benefits of a small epsilon. We just have to be somewhat close.
What is f sub s again?
That's just going to be evaluating it at time s.
Okay.
So at time 0, we're at f. At time 1, we're at f plus g.
Okay.
And this is some intermediate time. Okay. Is ft prime of z over ft of z, does this ever have any issues? Does the denominator ever blow up?
No.
Never, anywhere?
Is it greater than 0?
What's greater than or equal to?
No, it's always greater than 0.
Well, the question is, blow up where? I believe that there will be some values of z where this blows up. If f has a pole, if f has a 0, then this is going to blow up.
Yeah.
The whole point is I'm trying to count zeros of f plus g in terms of zeros of f. I expect f to have some zeros. I expect the denominator to blow up. Well, if I have something blowing up, couldn't that cause issues? Why isn't this bad? Does everyone agree that, for instance, let me take f of z is z to the n. This is a nice function. I think we can all locate its zeros. And so if I then wanted to shift and let g of z equals z to the 4th over 2014, this will satisfy all the conditions of Rouché. I'm using 2014 so I can reuse these lectures next year. Okay? So I could use Rouché and talk about that f plus g will have n roots inside the unit circle. But if I look at this, if I take z equals 0, this is going to blow up here. Why is that not a problem for this integral? There are points where ft of z blows up. There are points where fs of z blows up. Why is that not a problem for this integral?
They're finitely many.
I'm sorry?
They're finitely many.
Still a blow up. And maybe this one blows up and this one doesn't. Yes?
We already showed there can't be any zeros for f on the circle.
Excellent. We're only integrating on the circle. Right? It doesn't matter that this blows up inside the region. What only matters is where am I integrating. I'm integrating on this nice closed curve on that closed curve, there are no zeros or poles of my function. So this is going to be well behaved, this will be well behaved. We've got to be careful. We have to prove that ft of z doesn't have a 0 on the circle. What would it mean for ft of z to have a 0? If ft of z equals 0 on C, then the absolute value of f of z equals the absolute value of t times the absolute value of g of z will sum z and t in 0, 1. Can that happen? No, because we know the absolute value of f exceeds the absolute value of g. This can't happen. As the absolute value of f is greater than absolute value of g on C, can't happen. So this is never going to be 0 on the boundary. This will never be 0 on the boundary. Is this a continuous function? Yes. Is this a continuous function? Yeah. In fact, I can regard this whole thing as a function of just my parameter t. And I'm evaluating it at 2 close points. And so this is where you now just apply results from, standard, hopefully, results from real analysis. I have a continuous function on a compact set. I can use uniform continuity. I can find you give me an epsilon, I can find a delta so that if t minus s is sufficiently small, then the difference between these would be at most epsilon. And I'll just take epsilon to be basically less than 1 over the length of the circle. Okay? So the proof is now uniform continuity. you know, ft prime over ft is continuous. Given epsilon greater than 0, there exists a delta such that t minus s less than delta implies ft over ft prime minus fs prime over fs is less than the length of C divided by 2014. Do I need to divide by 2014? Whoops, I don't want length of C up top. 1 over 2014 times the length of C. Do I need to put in that fact of 2014? If it was just less than 1 over the length of C, I should be fine. I even get a 2 pi floating out over here. I like putting in a little bit of extra stuff just to give me a little wiggle room in case I forget a fact of 2 somewhere.
Is that a f of 1 there? F S.
Oh, sorry, that should be an f of s. Okay? And that's the proof of Rouché. Yes?
It seems to me that we never use the f is bigger than g in the circle, just on the boundary.
Correct. And the condition is assume f is greater than g on the circle.
Oh, just on the boundary.
Just on the boundary. So you're absolutely correct. That's exactly what you're supposed to be doing when you're seeing a proof. Do we ever use the assumption? Do you think that f will always be greater than f plus g or g inside the region? So let's think. This is a great question. Must f always be greater than f plus g inside? Well, if so, wherever f has a 0, then f plus g would have to have a 0, and g's zeros would have to occur exactly where f zeros are occurring. And so if you go back to our example over here, this would fail. You know, so f plus g should hopefully maybe be larger at some point. Well, for this one we might be particularly lucky because the zeros of g and the zeros of f, we'll be fine. Because f plus g, f of z plus g of z is going to be z to the n plus z to the 4th over 2014. How many zeros does this have at the origin? How many zeros does f plus g have at the origin?
1.
That's
4. Wait.
Can you answer this question? What's n?
It depends if n's bigger.
Yeah, if n is 8, it has 4 zeros at the origin. If n is 2, it has 2 zeros at the origin. So, number zeros at 0 for f plus g is the minimum of n4. So if n is very large, this only has 4 zeros at the origin. It has zeros elsewhere. And so you can try to play games. I think this is a good problem. Explicitly write down a function f and a function f plus g where f is greater than g on the boundary, but there will be some points interior where f plus g is larger than f. So what I really like about the proof is we're exploiting a really nice characterization of integer valued continuous functions. They're constant. And that's what makes the whole argument work. The difficulty is just doing some results from analysis. Is that I have 2 continuous functions. It's defined on a compact set. It's a set that has a finite length. And so I can use uniform continuity, I can use continuity results, and basically say this can't be too large. And so if I make s and t sufficiently close to each other, I see that they have to be the same value. So this proves that the function is continuous. And now that it's continuous, the only continuous function that's integer valued is that same value. So I could even drop the t subscript here. And so we get the number of zeros of f is the same as the number of zeros of f plus g. So problems to think about is, can you use this to give a proof of the fundamental theorem of algebra? Can you somehow take a function you know and tweak things a bit and use this to get a proof? Can you give me a function where you know how many zeros it has?
function?
Yeah. Give me a nice function where it's easy to calculate the zeros.
Uh,
Z to the
And
z to the n.
Yeah.
So if I give it a polynomial, if I start off with z to the n, I know it has n zeros. Can I tweak it to get to an arbitrary polynomial of degree n? And if so, that's another way to prove the fundamental theorem of algebra. So try to make that rigorous. Try to see if you can prove the fundamental theorem of algebra from Rouché's theorem. And if so, that would provide another proof of the fundamental theorem of algebra. And again, whenever you have a big result, you want to see how many different ways can you prove it. Your job is to let me know when the battery officially dies.
Okay.
Right now the battery's on 0, so. Alright, so this is the first of the three consequences of the argument principle. Second consequence is the open mapping theorem. Can someone tell me just roughly what does the open mapping theorem say? And whether or not you believe it's true for real value functions?
Maps open sets to open sets.
Maps open sets to open sets. Right? So, again, you have the standard requirement, let's have a holomorphic function. A holomorphic function will map open sets to open sets. What about the real variable analog? Do you think a differentiable, infinitely differentiable, whatever you want, real valued function maps open sets to open sets? So give me a counterexample.
sine and cosine. On the open set.
If you choose a sufficiently good open set, sines and cosines will work. Because sines and cosines will go from -1 to 1, you'll have a closed set. And so as long as your open set contains a period longer than 2 pi, you'll be fine. So one example is f of x is cosine x minus 4 pi less than equal to x less than equal to 4 pi. Sorry, strictly less than. So that takes an open set and maps it to a closed set. Another example which I like is g of x equals x squared, -1 less than x less than 1. And this maps the interval -1, 1 to the interval 0, 1. Okay. So the open mapping theorem is not going to be true in real valued functions. How many of you have taken a class in measure theory? Okay, so if you're taking a class in measure theory, you sometimes talk about what do measurable functions send open sets to? What do measurable functions send measurable sets to? That's a good thing to look at. For us, for complex, it's going to be different than the real case. And so for us, the open mapping theorem, F holomorphic on open omega, then the image f of omega is open. Okay? And again, you might say, well, great, who cares? Open sets are nice, and we'll see that this will immediately imply the maximum modulus principle. And the maximum modulus principle is extremely useful for trying to understand where interesting things happen for functions. Okay. You all, of course, have read the book's proof of the open mapping theorem. There is one place in the book's proof where I think they actually skip a step. They implicitly assume something can be done. This is one of the dangers when you read textbooks. All textbooks do this. You get into this habit after you've been in the subject for many years of not realizing that you've just assumed something. I remember the first time I was teaching this class, I was introducing another method of contour-integration. And I was looking at the notes, I found some notes from a colleague of mine in Bristol, and oh yeah, this will be no problem to present. And so I walk into class and I start presenting, and then I realize, oh, there's a highly technical argument to show that this term is small. And I've done this technical argument numerous times over the years. It's second nature now. We don't even write it down in our papers. But if you've never seen it before, all of a sudden what was supposed to be a 5-minute lecture became a 25 to 30-minute lecture to just very carefully go through all the steps and show that this doesn't matter. When you're reading proofs, it is very easy for small things to be assumed. And you want to be on your guard for that. Okay, so the open mapping theorem. So proof. So our goal is to show that the image is open. So all we have to do is take some point in the image and show that any point in the image close to that is hit. So try to draw a picture. Here's omega. We apply F. We get this beautiful F omega over here. I want to try to use the same notation in the book. All right, so we're going from the point Z, okay, and we're going to say, I think W naught is hit. Okay, so here's some point Z naught, and let's say W naught is the image of Z naught. So F of Z naught is W naught. What I have to do is show that I can find some small disk about W naught so that any W in that disk is hit by some Z over here. Where do you think that Z will live, roughly?
Small disk around Z naught.
Probably in a small disk around Z naught, right? It makes sense, you know, if Z naught is going to W naught, if I have some W close to W naught, I should have Z close to Z naught. That's where I'm going to be searching. What theorem do you think we're going to use here? So what theorem do you think is going to be useful for proving the open mapping theorem?
Rouché's theorem.
I'm sorry?
Rouché's theorem.
Rouché's theorem, right? There's a reason why we're doing the proofs in this order. What does Rouché's theorem tell us? So what information do we get from using Rouché's theorem?
Number of zeros of the sum of functions.
Good. The number of zeros of this function inside this region is equal to the number of zeros of this function inside that region. So we need to choose functions. In particular, we need to choose a function that has a zero. Can anybody think of a function related to f that will have a zero in a small disk about Z naught? I'm sorry? F minus omega naught. I'm not sure if it's an omega naught or if it's a W, so I'm kind of trying to hedge my bets in drawing. So I think this is a really good function to look at, because we know it has a zero in a small disk about Z naught. So again, I want you to get a sense of why we're arguing the way we're arguing in the book, why we're proving things. We want to use Rouché's theorem. If I'm going to use Rouché's theorem, I need a function where I can find a zero, where I can count and say it has to have a zero. Well, okay, so the goal is given omega close, and we'll define what close means later, to omega naught, find a z close to z naught such that f of z equals w, or omega. So this is going to be my function f. I'll use a capital letter here. I need to find some function g to add to it. And at the end of the day, I want to get a solution to f of z equals w. So what do you think I should add over here? What should my function g be?
Something involving W.
I'm sorry?
Something involving W.
Something involving w. What else should it involve?
Probably. F of Z in some way.
What do I want f plus g to equal?
F of Z minus W.
F of z minus w. I want this to equal f of z minus w. So I've got f of z minus w naught plus something equals f of z minus w.
It could just be W naught plus the W naught minus W.
So,
Wow.
right? So again, I want to try to emphasize the thought process behind what we're doing in the book. I want you to see that this is a natural thing to do. My goal is to get to f of z minus w, starting with f of z naught, f of z minus w naught. Because I know this has a root. This has the root z naught. And now this new function hopefully will have a root as well. Ah, that tells me w is hit. Okay? So this is a very natural thing to do. We know f has a 0. Big F has a 0 at z naught. And now we want to conclude that f plus g has a 0. You want to use Rouché to get f plus g has a 0, which would imply w is hit. So as long as we can do this for any w close to w naught, we win. Okay. Well, if we're going to do this, we have to make sure the conditions of Rouché are met. Right? What must be true? What do we need?
Holomorphic.
Need holomorphic. Holomorphic is no problem.
Okay.
This is a constant value function. And this is just a holomorphic function minus a constant.
We need that.
Holomorphic is no problem.
We need that f is strictly greater than, or f of z.
We need big F.
Yeah, to be strictly greater than.
Be strictly greater than big G. In other words, we need the absolute value of f of z minus w naught to be strictly greater than w naught minus w. So the holomorphic condition is no problem. The difficulty is, do we have big F greater than big G? This is going quite long on no battery. Okay. Well, let's think about this. What can you tell me about w naught minus w? Do you expect it to be big? Do you expect it to be small? Small. But all we have to do is get some small neighborhood about w naught. So we can make this as small as we want. Now, unfortunately, as this becomes small, what happens over here?
Also small.
Also small. But we have some control. We don't have to look at an extremely small neighborhood about z naught, right? Our goal is to just find some point in omega that's mapped to omega naught. So why not take a damn large neighborhood, technical term, about z naught? Don't let your neighborhood get small. Keep it large.
Sure.
Give us more points to look at. So now, can I ensure myself that in a small circle about z naught, that this is positive? So I claim there is a circle about z naught such that the absolute value of f of z minus w naught is strictly greater than, I want to just use the same number I'm using. I think I'm using delta. It doesn't matter what notation I'm using. It's strictly greater than, we'll say delta. Can I do that? Can I ensure that there's some circle where this is at least delta? What would happen if this wasn't the case? What if I couldn't find such a delta? What if on every circle there's always some point where it's 0?
Well, then there could be a point where that doesn't. The function is constant omega naught.
I'm sorry?
The function would be constant.
The function would be constant on a circle. So again, by standard results from analysis, I have a closed set. I have my circle. A continuous function on a closed compact set takes its maximum and minimum value. If that minimum value is not 0, hooray, I win. It's strictly bounded above from 0. That's my delta. The only danger is if every circle I draw about z naught, there's a special point where it's equal to 0. So maybe this is my sequence of points. What would happen? I would get an accumulation point. Does that contradict the open mapping theorem?
Yeah.
What conditions did we assume about f?
It's open or open set.
An open set, and what else do we assume about f? Holomorphic. Is it a contradiction to have f be constant? No. So what condition do we want to add to the open mapping theorem? It's not constant. So there's really, depends how you want to phrase it. There's either two ways to do this. The open mapping theorem either says, give me a non-constant function f, then blah, or if I apply a holomorphic function to an open set, I either get a point, because my function is constant, or I get an open set. I prefer to add the condition that the function has to be non-constant. But I want you to see from the proof how this condition naturally comes out. So this forces us to look at non-constant functions. So add the condition f is not constant to the statement of the open mapping theorem. Oops, whoa. Okay? So again, this is the point where the book glosses over it. If I couldn't find such a circle, I would have a chain of circles of small and smaller radii, and I would have a point of accumulation, and that would force my function to be constant. But I know that my function is not constant because I'm assuming it's not constant, so there has to be some circle where on that circle f of z minus w naught is greater than delta. What does that tell you about how large of a radius you want to take about w naught? So here's omega again, here's z naught. We have some circle now about z naught. And we know on the circle f of z minus w naught is greater than delta. Here is my omega, that's not my f of omega, here's my omega naught. How small of a circle do I want to take about w naught? A half of what?
Delta.
Yeah, if I take it to be half of delta, I've got, here's my function f of z minus omega naught. I want this to be greater than w minus omega naught minus w. And this holds on a circle about z naught if w naught minus w is less than delta over 2. So that tells us how small of a circle we want to take about w naught. So the interesting thing here is this could be a potentially large circle here. That's fine. That gives us just more points to look at. And now when we imply the image and look over here, w minus w naught is less than delta halves, which shows a really small circle. We can always do that. We can always shrink the circle about w naught. Because all we have to do is show that there's some arbitrarily small circle about w naught. Doesn't matter how big, such that every point is hit. And now, are the conditions of Rouché met? Yes. Conditions of Rouché are met. Therefore, f plus g has a root, and we're done. And that finishes the proof. Because what is big F plus g? Big F plus g is just f of z minus w. So we have f of z minus w has a root. Alright.
Can you explain one more time
Sure.
why like f of z minus w naught is greater than that holds on our circle when w naught minus w is less than delta over 2?
So this holds irregardless of w naught minus w.
Sure.
I just look at this and I say, I can choose some radius, some circle in omega such that f of z minus w naught is greater than delta.
Okay.
Now that I know how big that is, now I decide how big of a circle do I want about w naught.
Okay.
I want my circle so small that w naught minus w is going to be less than f of z minus w
I
naught
see.
on the boundary.
And we can just pick that then?
Yes.
That's fine?
We know that such a circle has to exist, otherwise there'd be a point of accumulation.
Right. Okay.
And so since there's no point of accumulation, I can find such a circle. So first I decide where I'm looking in omega space. Now that I know where I'm looking in omega space, now I decide how to localize in the image space. So there's a lot of stuff going on in this proof. It's a nice application of Rouché's theorem, but it takes a while to put things in place so that you can actually use Rouché's theorem. I need to have holomorphic functions. Not a big deal. The big deal is finding which holomorphic functions. Well, I'm trying to get f of z minus w. So if I'm trying to get f of z minus w, it becomes a really good idea to look at f of z minus w naught plus. And when I do all of this, this whole thing cancels and becomes just f of z minus w. That's my goal. That's what I want to look at. That's what I want to find a zero. Now, I'm a big fan of parentheses and grouping. How else could I group the parentheses here? You know, I've broken it up into this plus this. How else could I put the parentheses?
Could do.
When you look at these four terms, which two terms would you like to group together?
You could do f of z minus w plus.
Yeah.
'cause that is-
I've added
Yeah.
0. All I've really done here is I've written this as f of z minus w naught plus w naught minus w. I've added 0. Must be a good proof if I've added 0. Right? It's one of the few things we can do in mathematics. It's cleverly adding 0. It's adding 0 in such a way and then splitting it into two parts. That's what's going on here. Okay. Any questions on the open mapping theorem? So again, this is very different than the real case. The real case open sets are not mapped to open sets. And we gave an example when an open set was mapped to a closed set. We gave an example when it was mapped to a half open, half closed. Okay. What will probably happen is I'll run out of batteries and not be able to upload the file. So here we have time, I think, for one last one. The maximum modulus principle. So f is holomorphic on open omega, simple closed curve gamma inside omega with a nice interior. So think, the curve doesn't intersect. It splits the curve, it splits the plane into two regions. So here's gamma sitting inside my big omega. Okay? Then the maximum of the absolute value of f occurs on the boundary omega. Again, the maximum of absolute value of f on or in gamma. So what I'm saying is, you have some closed curve, it doesn't intersect itself, it divides the plane into two regions, the inside and the outside. When I range over all points on the curve or inside the curve, the place where absolute value of f is largest has to occur on the boundary. Could it also occur inside? Yes. And in fact, we'll see that the only way it can also occur inside is if the function's constant. If f is also maximized inside, then f is a constant. Well, if you think about it, if we had a whole string of places where the function f was constant, you'd have an accumulation point for f minus the constant. And so, if there are infinitely many points where f takes on the maximum value, then you're going to be okay. Did it just run out?
What?
Oh, it's running.
No.
Okay.
We had a light bulb moment.
So the question is, how do we prove this? What theorem do you think will be useful for proving this?
Probably
Open mapping, right? So using the open mapping theorem, we can prove this. Alright, so let's assume it's not true. So assume not. So here's my curve gamma. And let's say it's largest here at z naught. Okay? Let's assume the maximum value occurs in the interior. What does that mean? Well, there's two possibilities. Can we assume that the function is not constant, that we understand the constant case? Sure, assume not. Assume f isn't constant. Constant case is clear. Right? If the function is constant, does it take on its largest value on the boundary? Yes. takes on its largest value wherever you want it to take its largest value. Okay, so let's just worry about the case when f is not constant. Alright, so how would I use the open mapping theorem? What does the open mapping theorem tell me?
That it maps open to open.
It maps open to open. So where should I apply the open mapping theorem? At what point? At Z naught. So let's take a ball of some small radius epsilon about Z naught. So a ball of radius epsilon about Z naught. What can you tell me about the image of this ball?
The image of the ball. It's
Yeah.
open.
It's open. Is open by the open mapping theorem. If you think about what's going on, let's say this is the point f of Z naught, where the function is largest. I'll draw the origin of the complex plane over here for simplicity. Doesn't really matter where I draw it. We know the image of the ball is some disk. You know, it's open, so it has to contain a disk, right? So since it's open, contains a disk. Since open, there is a small ball about f of Z naught contained in f of the ball of radius epsilon about Z naught. Well, draw the line from the origin.
Well, are you saying that you can have like a larger
Yes, that's what we're about to
value by
get.
just moving from
Yes.
Okay.
And I'm going to tell you exactly which direction to move away.
Other-
Yes, draw the line from the origin to your point and keep walking. You've just gotten to a value whose absolute value is larger. Walk in the direction from origin to f of Z naught. After going through all the technicalities of the proof of the open mapping theorem, it's nice to have a proof that is this elegant and simple. Just walk in this direction and it'll be larger. So, because this is open, I've just found a value where, when I apply f, I get a larger value for the absolute value of f. I'm further from the origin. Done. This is a contradiction. So we now know that any holomorphic function attains its maximum on the boundary. This would be a very useful function, a very useful fact about holomorphic functions when we prove the Riemann mapping theorem. So again, the Riemann mapping theorem is one of the gems for the course. It's one of the things we're building up to. I'll go ahead, so we start 1 minute. Right. You give me any region like this, and there's an infinitely differentiable holomorphic map between that and the unit disk. And in fact, even in a case like this, I can even extend the map to be from boundary to boundary. Infinitely differentiably. Now again, I may lose some of the infinite differentiable as I go up to the boundary. But it's absolutely amazing that we have a result like this. I can take this region and map it to this region. Why do you care about this? Who are my physicists again? You can reduce problems to, if you do all these cylinder problems and all these other things, you can reduce it to one region. You learn one set of special functions. You learn one set of integration techniques because of the symmetries. And now everything has that, and then you just invert to go backwards. Because it's infinitely differentiable, it actually has its inverse. Okay? Nice result to get. Okay, so this finishes up all of our stuff on the big three consequences of open mapping. So there is zero chance of Monday being Mountain Day unless the president really makes a mistake. So we will continue and we'll do section 5 very briefly, and then we'll go into section 6, the complex logarithm. Okay.